Okay, welcome back and welcome to lecture number 2 on operating system structures. Last time we did chapter 1, which was on an overview of operating systems. So to move right along to operating system structures, chapter 2 is kind of an interesting one. There's a little bit of overlap with chapter 1. Looks at operating system services, interfaces, system calls, types of system calls, systems programs. So really focusing today on the concept of the system call interface, the APIs, and looking at the virtual machines as well. I'll touch a little bit upon that, and then some of the generations, and then a little bit on the boot process. So describing the services an operating system provides its users, processes, and other systems, and discussing the various different ways of structuring an operating system is also a focus for today in terms of the objectives, and explaining how one boots up, initialized, and etc. and so forth. So let's get right into it. Services. And the one thing people usually judge all operating systems by is its interface, human-computer interface. And as the slide kind of suggests here, we have different types. We really only have 2 that we've actually formalized in terms of human-computer interfaces. That would be the CLI, or command line interface, and then the other one, the GUI, or GUI, as most people know, graphical user interface. We also have batch interfaces. We have no interface. We can have an operating system without an interface. We don't necessarily require one. So one set of operations or services is just the user interface, whether it be UI in terms of user interface, whether it be CLI or GUI in terms of command line or graphic. The other main function that an operating system normally does is execute programs. So we consider, we can consider program execution as probably the main task. Why people use computers, so they can run Microsoft Office, Word, email programs and stuff. So executing those programs is a big one. I/O operations as well, being able to read and write to USB drives, to CD-ROM drives, hard drives, all sorts of input and output operations, and then file system manipulation. What else do we have on a computer outside of programs? We have program files. So these would be Word files, Excel, PowerPoint, all sorts of different files themselves in terms of what the operating system is going to do. So one set of operating system services also functions to help the user in terms of communications. So we have processes that exchange information back and forth to create what's called a networked environment. So our operating system facilitates the network or establishes communication protocols. Communications may vary from shared memory all the way through message passing packets. They're moving across the operating system from one system to another. Another thing the operating system normally does, but although the users don't really like it, is error detection. So if there's the fatal blue screen of death, the error messages, all those little things that come out. Usually some of the error messages are caused by the operating system, but most of them are caused by user programs or by network failures or something of that nature. So error detection is also one of the things the operating system needs to constantly be aware of. And it may occur in the CPU and in the memory hardware, I/O devices, user programs. So it might occur everywhere, not just in the operating system itself. So debugging facilities can greatly enhance users' programmable abilities as well to efficiently use the operating system. Most people don't really bother with the debugging facilities. The Dr. Watson and all the other things. In fact, a lot of people don't even know that we actually have debugging facilities in the operating system. Because most people don't ever have a need. They just reboot the computer and fix it. But sometimes you want to figure out, well, what caused the error? And in older, like DOS operating systems, with command line interfaces, we could run a debugger. We could figure out what happened, look at core dumps and stuff, and kind of analyze things. Now, with graphical user interfaces and everything of that nature, we don't really care. Instead, we just close it down, just stop it, start it again. If it doesn't work again, we just reboot the computer. So that's pretty much our error detection. But in the old days, it was kind of imagined that users would want to do debugging of the operating system. So some actually do have debugging facilities. I know that every operating system that runs on a UNIX platform has UNIX debugging facilities for the telecommunications. As an example, being able to ping another server to see if it's awake, being able to see what your IP, running IP config or something of that nature, see what kind of ports you've got configured, to manually basically, I wouldn't call it debug, it was more lines of configuring your interface. More sets of operating system services. One would be for sharing resources. So as a resource sharer, we have a resource allocator. So when multiple users or multiple jobs are running concurrently, resources can be shared between them. So we have the sharing of everything, and everything's a resource. There's many different types of resources. The biggest one that we're going to be concerned with in terms of the lecture material is going to be the CPU and the memory, which is a shared resource for everything. We'll also look at file storage in this class as well. But to be able to allocate memory, to be able to allocate CPU clock ticks efficiently so that the operating system can share those resources among all the running processes makes a lot of sense. The operating system is also responsible for accounting for the most part. And the accounting is to keep track of how many users are involved, logged in, what resources are they using, what protection, things of that nature that the operating system might provide. We also have a separate category here for protection and security. In terms of protection and security, the operating system is supposed to be providing this. So we have user logins, we have built-in firewall as an example. And in the past, though, however, especially Microsoft operating systems have been kind of short of all three. Kind of short on the accounting part, kind of short on protection and security in terms of features. Although through each new version of Windows, we've had some benefits or some improvements, I should say. The command line interface also allows direct command entry, something that's implemented in the kernel, and it's sometimes by the system programs. So we can bring up a command prompt shell, also sometimes called a shell, and entering commands to ask the kernel to do something, to run a program, to open a file, print a file, do all sorts of different utilities. Primarily fetches a command from the user and executes the command. So sometimes called built-in, sometimes also names of programs and things. In the latter, adding a new feature doesn't require a shell modification. We just use a generic shell, which is kind of like if you think about it, the graphical user interface is sort of a shell. In fact, it's just a window version, graphic version of a command line prompt. Instead of typing in names of files, we're double-clicking on them to select them. So it's kind of different, but still one and the same. We have the concept of the desktop metaphor for the interface, which we've seen in a lot of different operating systems, usually using a mouse, a keyboard, a monitor. Icons representing files, programs, actions. Kind of interesting, we still have a desktop metaphor as well as icons, even on Android operating systems. If you've noticed your smartphones, your tablets, they just have a bunch of icons on there. And you tap with your finger on the icon and it opens up. Same thing as Windows, actually, if you think about it, except for instead of using a mouse, you're using your fingers. But the metaphor, that desktop, and then we have multiple desktops. Well, we actually have that on computers too, which just nobody ever uses it. But you could have multiple desktops and put all your icons on there. There's also a file manager. Actually, you can download file managers for the Android phones. So in a lot of ways, the operating system on a tablet running Android is actually kind of sophisticated compared to, let's say, the primitive Palm Pilot software of the past, or some of the Windows CE version and stuff like that. So it's pretty sophisticated. In fact, there's talks about making, and there's a couple of companies that are coming out with models that are desktop computers with Android on it. So instead of having Windows, you've got Android. If you think of the possibilities, it actually creates a very fast-running operating system. And if you can get Microsoft Office compatibility, what's the difference between using that versus Windows? You're web surfing, you're checking email, you're opening up documents, writing documents. For the average computer user, it's pretty similar, I should say. So there's a lot of speculation that the Android market is going to hit desktop. Well, all you have to do is take a tablet and connect a Bluetooth keyboard to it, and you've got a desktop. So in a lot of ways, it's already hit. So we have icons representing programs, files, and actions, various different mouse movements. The concept of the folder, keeping directories, open directory and information, in terms of folders and files. Invented by Xerox PARC, believe it or not. Actually, the first version of Windows, if you go back to there used to be a Channel 9 Discovery Channel. No, it was PBS, Channel 9 local station that did the making of Windows, or the history of Silicon Valley. And it shows a couple people from Microsoft walking through Xerox PARC, and then that's where they came out with the concept for Windows 3.0, essentially. So I don't know. Who knows what really happened? But they've been trying to take credit for it for years. So many systems now also include both together, command line interface as well as the GUI. So Microsoft Windows has both of them. Apple OS X has both of them. Has a GUI interface as well as a UNIX kernel underneath the shell. And then Solaris also has both of them. And then we have this thing, if you've ever worked on a Linux system, you know that we have many different desktops that we can load, like KDE, Chrome, some of the other ones. There's a Java desktop actually out there that you can actually load on top of a kernel, essentially. And if you think of the concept, Windows is nothing more than a desktop. So is the OS X. And the desktop is nothing more than the GUI interface, command interface to the computer, to the kernel. And speaking of interfaces, this is how we speak with the kernel using system calls. So programming interfaces to services that are provided by the operating system fall into the category of a system call. Typically, these system calls are written in C or C++, mostly accessed by programs using an API. And I think I may have mentioned this last week as well. So we have an application programming interface rather than the direct system call use itself. An example of this would be like system I/O, so printf, scanf, cin, cout, C++, that basically are higher level calls like printf as a function call that's implemented with a lower level. Well, printf is going to be output, so it's going to be, you know, write this, write this, write this. A bunch of writes along with some buffered memory and along with a routine or an algorithm to facilitate multiple writes so we can write the output to the screen, maybe line by line or word by word. So the API raises the level of abstraction, makes it easier to actually use the system call, makes it more functional, adds features to it. So three most common APIs are the Win32 API for Windows, POSIX API or POSIX-based system for Linux and Unix, including virtually all of the Unix versions of Linux, and Mac OS X uses the POSIX-based system. And then we have the Java API for the Java Virtual Machine, or JVM. Java is actually an operating system in itself. So when you run Java programs, you actually are loading an operating system on top of an operating system, and you're loading the programs inside the Java operating system. So why use APIs rather than system calls? It automates the work. It's a little easier. It combines a lot of different system calls together into one call. Makes it a lot faster. And note the name system call. Names used throughout the text are generic in terms of the system call. So read or write would be a generic type of system call, is what that's referring to. Here's an example of system call. System call has a sequence of to copy the contents of one file to another. So this would be a CP command in Unix, or a copy, DOS, Windows. So we have a source file and we have a destination file. And then the system call sequence that would be part of the copy. And imagine copy is just one word, or CP is just one word you're typing in. You know, CP space, source space, destination. So all of these things here would be part of the system call interface that would be implemented when you ran the CP command. So you have to, acquire the input file name, write a prompt to the screen, accept the input file name, acquire the output one, open the file if it doesn't exist, abort if it does, create an output file, and go through all these different things, and then finally at the end, transfer everything over, read and write, and then terminate normally. So all this is pretty much automation, is what I was referring to in terms of why we write higher level APIs for system calls, so that we can write a ton of system calls, use some memory, variables, and actually create a program out of it. And think about it, the CP, is a copy command called CP in Unix, is a program. It's a self-running program that copies files from one location to another. Here's an example of a standard API. Consider the read file function. And the read file function is in, let's say, a Windows Win32 API. So the function for reading from a file. And so we have a return value. Here is going to be bool. And the name of the, I can shut that door if it gets too loud, read file, or kind of rude, function name. And then some parameters that go along with it. And then a description of the parameters passed by read file. We've got, file handlers, we've got pointers to certain pieces of memory, etc. and so forth. But what we've got is kind of a packaging of a lot of information in terms of the function call. And so in system call implementation, we've got a number of associated with each one of the system calls. When we run the system call, it goes down to the kernel, and then the number that's associated with it says, let's say, for example, it's read file. It's associated with the kernel in terms of a table structure. So this is number 955. Oh, okay. And then it runs its routine, its internal code to process 955, which is a system call. So we put character numbers on it, or letters on it. We call it things that we can understand from human perspective, like read file. The kernel puts a number on it, keeps it in a system call interface table. So it maintains a table indexing according to these particular numbers. When the system call invokes intended system call in the operating system kernel and returns the status of the system call and its return value. So if it was successful, it comes back with a 0. If it erred, it has a -1 or something. Or, in fact, these are just arbitrary numbers. Anything that you configured for the kernel, if you were to configure it, most likely you'd probably keep the default behavior, default return values. But the concept of there being a return value coming out of that system call is important because that's how we do error checking or debugging from an application programming interface. So the caller need not know nothing about the system call that's being implemented. So we have a little bit of abstraction, along with some information hiding in terms of what does that system call actually do? Well, we don't care, it just reads a file. Just copy here, CP copies a file. Open opens the CD-ROM, so we basically use blindly without having to worry about it. You just need to obey the API and understand what the operating system will do as a result call, what you're expecting back. Most details of the operating system information interface are hidden from the programmer, and they're hidden by the API. So managed by runtime support, set of functions into the libraries that are inside of the compiler. So we have runtime support for stdio as an example to read and write to the standard output, get information from the keyboard. And that's actually implemented by function calls. So here's an operating system relationship with the API to the system call to the operating system. So this is kind of like what I drew last week. I took this box, put a line down the center and called this the system call interface. When this cloud up here isn't really a cloud computing, it's just kind of like the user application. And the user application comes down, performs an open system call from user mode. The open system call goes through here. It goes down in the system call table and says open is number 1 or 2 or 3, finds the associated number that goes with that open, translates it and runs the instructions that are related to that particular call. So open is going to be implemented by the open system call. And then there's a return that comes back up through the kernel mode and passes through the interface to the user, and you get, okay, open, 0. We're done. It completed properly for something. And here's our standard C library, where we've got an example of a C program invoking printf, which is a library call, also part of an API by terminology, which calls write, which is the system call to write to the standard output. And then here we have, includes stdio.h, tongue twister, and then we have printf, greetings, and some code. When this is called, it goes down here and says, oh, this is right. Write the system call, come back up. This is basically how our function calls are working in C. And you can probably get an impression now in terms of earlier Linux and Unix versions, and even modern day Linux and Unix, that's written in C that facilitates C system call interface, where we have the higher level C language programming with higher level APIs that are basically just running system calls. And then at that point, you're doing what's called systems programming for the most part, because you're running system calls. So the difference between application, user programming, and systems programming is the type of application that you're running and whether or not you're executing system calls through that interface. So the system call parameter passing, this is when we take the parameter greetings and we send it to printf. So we have greetings as the parameter that's being sent. Often more information is required than simply to identify the desired system call. Instead, we extract the type, the amount of information. That's going to vary according to the operating system and the call. Some calls take one parameter, some take 2, 3. Depends on what we're doing. 3 general methods used to pass and this is for passing the parameters to the operating system. The simplest method is to pass the parameters in registers. Load them up in memory so that they're available. Put them in a register. Some cases may be more parameters than registers. Depends upon the register size and configuration of the hardware. Parameters are stored in a block or maybe a table in memory, and then address the block by passing the parameters into a register. So putting them in like a temporary storing place that says, okay, these are all the parameters that are associated with the system calls that are going to be run. And that's the approach taken by Linux and Solaris and the Mac OS X. In fact, we don't actually have a system call interface on Windows. It doesn't exist. So it is implemented in the APIs, but we can't run a system call in Linux. There's too much protection on the kernel. And the kernel has kind of a slightly different way of working with the user. It's doing a lot more automation for the user than it would be in a UNIX and Linux environment. So the parameters are placed or they're pushed onto a stack by the program, and then they're popped off of the stack by the operating system. And then we have the block and the stack methods that do not limit the number or length of the parameters being passed. So here's a parameter passing via a table where we have a user program that's running a system call, and X has got parameters for the call, let's say. We load the address X, we use the system call, let's say it ended up being number 13. So on the operating system's point of view, use the parameters from the table that are associated with X. And here's the code for the system call number 13. As I remembered before, system call number 13 is just the kernel's abstraction. This is where the 13 came from. It said that this is an open, a close, or whatever. Open the CD-ROM drive, access the hard drive, whatever happens to be the activity associated with the number that's going to be performed by the operating system. So we can load it in a register which is accessible by the operating system, or we can load it in memory. So if we load it in memory, it takes up memory. If we load it in the registers, it takes up registers. So it's half a dozen and other reasons why you want to use one or the other. So types of system calls. We have system calls to control processes, which is the theme for the next chapter, actually, chapter 3. They're also done for file management, for device management, information maintenance, and also for communications. We have system calls that open up sockets and send and receive through socket interfaces for communication protocols. From an MS-DOS execution perspective, we've got A and B running here, and A is at system startup and B is a running program. And what ends up happening is we get a bunch of processes that get loaded, and here's our free memory, kernel, command line, interpreter. Think of this like the command line interface, and then we have memory. And so here we've got a loaded process. We loaded up Microsoft Word as an example, and then another loaded process would load on top of that, and then another one would load on top of that. Processes actually are kept separately as well. They don't share memory, they don't overlap into other memory spaces. They all fit into memory, miraculously, which is why we have memory managers that work in operating systems. And each process is keeping track, or excuse me, the kernel is keeping track of which system calls were sent by which process, so it can return status to whatever process actually made the system call in terms of the processing. There's a FreeBSD running multiple programs, kind of the same concept, where we have free memory that's a buffer in between that the process might be using. So it depends on the operating system and the implementation as to how the memory is going to be organized, which order the processes end up in memory, and how the memory is actually allocated for system call, send and receive, and which system calls are actually, can be made available for the operating system. So this concept of systems programs, as I mentioned before, they provide a convenient environment for the program development execution that can be divided into a couple of different categories. So a systems program, as I mentioned, or defined for you, is one in which used system call interfaces or kernel utilities. So it's a program written in user mode that runs, that manipulates the kernel, talks to the kernel, versus, let's say, Microsoft Word, which is a word processing program, or QuickBooks, or accounting program of something of that nature that runs a user task. So systems programs are designed to communicate with the kernel for the most part. And the categories for file manipulation, status information, file modification, programming language support, loading and executing programs, communications and applied programs. So the kernel can actually have systems programs, and as an example of that copy program we looked at earlier, the CP command or the copy command is a kernel level systems program. It's used to copy one file from one location to another. Same thing with the delete one file, delete a directory, or rename a file, rename a directory. Those would be referred to as systems programs. And just because they exist and they're run with a kernel doesn't mean the user can't create them. The user can create as many systems programs as they want. Most users view the operating system, their view of it is defined by the systems programs, not actually the actual systems calls, but the programs that they're running. As an example, the CP command defines your interface with the operating system to copy a file. So there's a Solaris 10 dtrace following a system call. It's basically going through and looking at different events that are queued up that occur. You have to think about the concept the system call is actually running a lot of different things. It's not just running an open. There's no such thing as an open command, actually. To open something. That's a user level system call command that probably has maybe 20, 25 instructions to it that's being run. And this is kind of an example of kind of a trace of all of the different things that might occur in terms of events that are queued up for that open. And for the purposes of this class, you don't need to know what the dtraces look like or what traces are all about or anything of that nature. It's just to illustrate a point that although open is one command, it's really about 15 or 20 smaller kernel level instructions that are being run to actually perform that open, as we're calling it. And then imagine what, like, say, fopen might be, and that's like an open with a bunch of other stuff associated with it. And fopen, if you're not familiar, is a higher level API that's running a system called open. That's file open. So it depends upon your abstraction. At a higher level you come up, you got more functionality associated with one word, if you think about it. So let's see, system programs provide a convenience environment for program development and execution. Some are very simple user interfaces to system calls, others are more complex. In terms of file management, to create, to delete, as I mentioned before, to copy, rename, dump, list, those would be generic manipulation commands. Status information, some ask for information about the date, the time, those would be system programs to return the date, to return the uptime, to return log information for debugging and stuff like that, performance, how fast are we running, what's our CPU utilization going on right now. Typically these programs help the print and the output of the terminal of other devices as well. And some systems are implement a registry used to store and retrieve configuration information. This is actually kind of like where we get the registry from in Windows. We don't have a registry. In fact, I forgot about the registry actually. We still have it in Windows 7? We still have a registry? Yeah. Most users are taught, stay away from that, don't edit the registry. In the old days, people tried to edit the registry when it first came out. Problem is keeping configuration information for system calls that the kernel is using, that's doing. So you mess up the configuration, you've messed up the system calls. Now your hard drive's not going to work, or your operating system's not going to be stable. And a lot of people used to worry about, oh, there's stuff in the registry that doesn't need to be in there anymore. Leave it alone. Unless it's using it, it's not even accessing it, doesn't even know it's there. So it's not really something that has to be modified by the user, as an example. So in terms of file modification, text editors can create and modify the files themselves, special commands for searching contents of files, performing transformation on the text, copying things, editing. Programming language support may also exist for compilers, assemblers. In fact, there's a ton of debugging and interpreters sometimes provided. And that's where we get like the Linux environment with a GCC compiler, where we can, and in fact we have like C shells, where you can type in C commands and use the C programming language in a shell environment on top of the operating system, and actually call system calls and do a bunch of talking to the kernel directly. So you can communicate without having to go through an API if you wanted to. Or you can use the APIs through the shell as well. Loading, unloading, absolute loaders, relocators, linkers, editors. A lot of these tools here in this category are kind of combined with our modern day programming languages. Most of our languages do that. We don't even think about it anymore. We just click on compile. In the old days, we had to create object code, link the object code together, set parameters for the configuration, for where we want to find what directories we're going to use, and then, if you were using shared objects, you had even more commands to put in there. We had these make files that we put together to give us our configuration for how we're going to make that program work in terms of the executable file, what should be included in there. Now it's easier. We just click on run, compile, in a GUI line compiler. And it does everything for us. We don't have to worry about half that stuff, which makes it easier. So you don't really have to be a true computer scientist these days to do programming. It's kind of unrelated, actually. It's more like running a program. More like creating a PowerPoint presentation to a certain extent. Okay, communications. Providing mechanism for creating virtual connections among processes, users. Computer systems actually creating a multi-threaded environment, allowing users to send messages to one another on the screen, browse web pages, send electronic mail, do all sorts of things. Those are services by system programs. As an example, your email client, your Microsoft Outlook, your Gmail through Thunderbird or whatever. It's running system calls. All these programs are nothing more than GUI interfaces on top of system calls to send and receive your mail through your ports. And you use this SMTP server that's associated with your account on this network. And the system call is actually sending and receiving your messages. The GUI that you're using, Outlook Express, your Microsoft Outlook, your Thunderbird, whatever email client you're using, nothing more than a higher level abstraction built on top of that interface. Just there to automate your environment for you. So if you think of content, we've come a long ways in terms of automation. The whole GUI interface, which is great. Because one of the barriers, especially in the beginning of computing, for personal computing, was how do we get the operating system to be more user-friendly? Could you imagine if if Windows never came around? Most users started using computers when Windows came around and went, oh, it's easy. You just click here. You just click there. There's nothing to remember. There's no skill involved in terms of the operation of that computer. Prior to Windows, there was an actual skill and a learning curve. You had to learn a bunch of commands in order to use the commands, and then you had to format, your whole file system was your own design, and your whole use of the computer was essentially your own design. And, people used to tape stuff to their keyboard, remember commands and stuff. And a lot more work invested in the operation. Now we just buy a computer, take it out of the box, turn it on, and start sending and receiving email. Already even configured for us already, too. We just turn it. It's like an appliance now, actually. So I say to people who are afraid of computers, and believe it or not, you guys aren't, but there's a generation of Americans that are completely afraid, still afraid of computers. Actually, I used to say multiple generations. It's not the young kids, actually it's like people my age, a little bit older, who are they're terrified of computers. They don't understand like how easy it really is. They think it takes like intelligence or something. And computer people, like now computer people, everyone's a computer person. I'd be surprised to run across anyone, especially in the state of California, who doesn't have a computer, who's never seen one. Especially if they're in high school or they just graduated from high school. The last couple of generations, they all have computers these days. But believe it or not, there was a time in America when we didn't have it, and elsewhere we didn't have computers. In fact, I remember my first computer that I bought. It was $3,000, and it didn't even have Windows on it. It had DOS on it. It was a glorified word processor. What it was, and all I had was I had a printer, and I could use it like an electronic typewriter, which was fascinating because it was worth $3,000 at the time. It was like the price of a car. It was worth that, not to have to use correction fluid on a typewriter. And it cut down and made life easier to be able to print out a document instead of having to type it. Now people use computers for connectivity. I think, word processing, they just take for granted these days. If you took away computers and gave everybody a typewriter, then they'd appreciate it more. And there's generations of people who've never actually seen or used a typewriter, which is kind of interesting. But now computers have the biggest thing now is connectivity. Connectivity to social networking, connectivity to email, communications. It's more of a communications tool than it is a typewriter these days, which is kind of interesting. Which is how we have the whole tablet industry. It's all based on communication, sharing videos, sharing pictures, files, and things. So, it's like tangent, but it was basically showing a point of usability in the command line interfaces and GUI interfaces. So the system design and the implementation of the operating system design and the implementation of the OS is not solvable, but some approaches have been proven successful, some have been unsuccessful. So all that little tangent I went on was actually related to what I'm talking about next in terms of the design. If we have a microwave oven, we don't need to check email on it. we have a computer, it's an operating system, and its purpose is to heat an environment. So it has to detect the door open, the door closed. It has to have, some sort of a touch interface or some sort of button or a dial. Actually, older microwaves have dials on them. Now, actually, they're all electronic. So now you can probably, and actually, they should be connected on the network these days too. So like a coffee pots, wake up in the morning, press a button, from your office. I want coffee. And the machine just makes coffee for you, And that happens. And there's an operating system on that coffee machine as well. So the design of Windows made personal computers more usable. Android operating system made tablets and phones more usable. Internal structures of different operating systems, they can vary widely. In fact, just comparing Android with itself, the older versions versus the newer versions is completely different, actually. Better. The new is actually faster and better than the older versions. So we have different implementations. They start by defining the goals and the specifications. What are we going to use this operating system for? And then kind of work from it from there. Affected by choice of hardware, the type of system that can be implemented. In the old days, the tablets couldn't load Windows. Now we actually have Windows 7 models out of tablets, which are not bad. But why would you load Windows 7 on a tablet? The thing only gets like 2 or 3 hours of life anyway. So, unless you had a tablet that ran for, 200 hours or so, that ran Windows, that would be perfect. But why do you want Windows? So it's interesting, because if people learn an operating system, I'm kind of going into the philosophy of operating systems now. They learn an operating system and they don't want to switch from it. So there's a whole consumer market out there for Windows tablets. Because they don't like iPad, they don't want to adapt. And actually, believe it or not, a lot of people don't get iPads because they don't know. They're not familiar with the operating system. not familiar with the interface, they don't know if they're going to like it, or they do get it and they don't like it. So, but if you think of the concept, what I've been saying since the beginning of this lecture, they're all doing the same thing these days. Well, what do you use the thing for? I mean, unless you're going to use it for something that you have to have Windows for, why do you need Windows? You can still browse the internet, use web browsers, Flash on these current Android tablets, not on the Apple. And that's one of the big problems, I think, in terms of the decision making. Let's say you're a user and you're going to go out to buy a tablet. Which operating system do you want? You know. And if you're a tablet user and you're going to use it for the tablet, you're going to want the one that's going to give you the most battery life, which is going to be Android. Why would you want 7 on a tablet? Because if that's the case, you might as well just get a notebook computer. Because what you really want is a notebook operating system, you know. So, but you see them, I've seen them, they have like little keyboards. They look like notebook computers. There's a Acer, I think, makes it, or Iconic Tab or something. It has like a Bluetooth keyboard that the tablet sits into, and it looks like a notebook computer. And I'm thinking, if you're going to carry that around, you might as well just carry around a notebook computer. But anyway, slight tangent, but the goals of the operating system, what you need it for, is a consideration in terms of what goes into it, as well as the hardware choices. So the affecting choices of the hardware, the type of system that can run on it effectively, is a consideration. User goals and system goals. So we have kind of two, they should be on the same lines, and they pretty much are. The system goal is to stay up as long as possible and conserve battery life and provide services to the user. And the services are going to be for connectivity, for email, for internet, for 3G, for whatever it has to do. The user goal is the operating system is, is it convenient for us to use, easy to learn, reliable, safe, and fast? Can I check email on it? Can I do everything my desktop can do? So that's what the user goal is in the system. They shouldn't be combative. They shouldn't be they should be together towards the same goal. Make it easier to use, error-free, efficient, things of that nature. So important principle to separate policy versus mechanism. Policy is what will be done. Mechanism is going to how do you do it. So what's going to be done? Well, we need internet connectivity. So we put Wi-Fi on it. And how are you going to do it? Hardware device. Put Wi-Fi on it. Wi-Fi signal actually eats up memory. Everyone knows that probably. So it's like we'll make a feature so that the user can shut it off. More so than on a desktop computer. Because on a desktop, people are going to be connected to the wall most of the time. They're not going to worry about battery life. So, mechanisms determine how to do something. Policies decide what will be done. So the policy might be, we need an on-off switch. And the mechanism from a user's perspective. In fact, I like them. There's new tablets out with buttons. Why do you have to turn the thing on? You go to the interface to turn off the Wi-Fi or to turn off the screen lock or whatever. You just flip a button on the side. Yep, Wi-Fi's off. It's like turning pieces of it off so you don't have to worry about the battery. So when we're ready to use it again, turn it back on. I think so. Which is kind of revolutionizing the concept as well. Mechanisms actually for USB ports and stuff like that now. It's like, why make everything Bluetooth? Bluetooth wears your battery down too. So why not just put USB ports on the side of it? So separation of the policy and the mechanism is a very important principle. Allows maximum flexibility if the policy decisions are to change later. You want to change it. In terms of a simple structure, MS-DOS written to provide the most functionality in the least amount of space. It didn't take up very much room and had a lot of functionality. MS-DOS actually runs pretty fast. No dividing of modules. It's DOS or no DOS. You installed it, you got a kernel, and the kernel had everything inside of it. Still has everything inside of it. In fact, we still have DOS. We're still working with DOS, disk-based operating system. Although MS-DOS has some structures, its interfaces and levels of functionality are not well separated. It's built in, so that's why we can't just take, to some extent, a Windows 7 machine. Actually, we can't because it's backward compatible to XP, but we can't turn it into something else. Like you can with, let's say, a Linux kernel, when you can load a KDE desktop or a GNOME desktop, or other modules can be added to it. So here's our MS-DOS layering structure to compare it. Because MS-DOS is kind of the simplest operating system to sort of compare. We have our ROM BIOS, our device drivers. We have our MS-DOS drivers, our command.com, our interpreter, and we have all the other drivers that go along with it. Our resident system programs, and we have application programs that run on top of it. This is pretty much how Windows is running as well, except for there's a few more layers in the interface. So a lot of people consider and they define operating systems by a layering approach, using layers for the structure. And the layering approach is divided into a number of levels, each built on top of lower levels. And the bottom level is usually 0, which is the hardware. And the highest level is the user interface, or the user mode, if you want to call it that. So it gives us modularity, so we can select different functions or operations and services that are only for different levels, and consider we can swap out this layer with another layer of resident system programs, or maybe the application program layer. We can swap it out with other application programs, stuff of that nature. So it allows for flexibility, modularization of the operating system. Instead of just taking this whole big box and calling it the OS, and not layering it out, means we can't fix anything, we can't modify anything. MS-DOS is actually pretty layered. Windows is even more layered. Windows, all of the shared libraries are in a separate DLL kind of configuration, separate directory. The registry keeps track of all the configuration, that's a layer. The drivers themselves, the lower level drivers, are loaded on in a separate layer of abstraction. So here's another layered operating system. This one's kind of done in a circular motion rather than a pyramid. We've got the inner hardware. We've got layer 1, layer 2, layer 3, layer 4, layer 5, all the way out to layer N, the user interface, which is usually the last layer. And this is kind of like why they call this the kernel. Not really the hardware, but let's say over here is the kernel, which is on top of the hardware. If you take the hardware out and actually consider it, the innermost intercenter piece of the operating system is generally referred to as the kernel. It's the lowest level of abstraction and layering, usually around layer 1 or so, layer 0. And it's the most functional in terms of what we're calling the operating system. And then the farther we get out in the abstraction, the more user mode we get. And the less of the operating system, more of the user's experience. So here's Unix. Compared to us with Unix. Unix is limited by the hardware functionality as well. Original Unix operating system had limited structuring. Unix OS consists of 2 separate parts. We had the systems programs and we had the kernel. Unix was actually designed to run on different hardware. In fact, today it still runs on non-PC, non-personal computer hardware. Linux runs on personal computer hardware. So Linux is the version of Unix that's designed to run for personal computers. Otherwise, Unix, we have Unix servers supporting client server or peer-to-peer or distributed. So we have like huge Sun systems. These Sun systems are business equipment, business machines. Not to be confused with a mainframe. Mainframe is the old terminology for the all-in-one computer mainframe, server slash database slash everything. Huge computer in terms of not necessarily size, although people, when you think of mainframe, they always think about, it's big in size. Not that big. It doesn't have to do with the size. It's more along the functionality is huge. Server functionality is huge. So the internet is all Unix servers. So we go to an ISP. We go to Google. Actually, not an ISP. We go to a service like Google or Yahoo or Facebook or Gmail. Actually, Gmail is off on separate servers too. In fact, Google's dissected out into different, and we're logging into Unix servers. And the Unix server is providing the functionality that we're needing. And the server itself, by concept, serves up. So we have interfaces and multiple connections. PCs never were designed for multiple connections, or for internet use, actually. They've been adapted as internet clients, which is really why they're referred to as client machines, client tabs, tablets. Email client runs on a personal computer. connects to a server that has email SMTP server support that serves up for emails that the client is requesting. So Unix is a bigger system. It has systems programs. The kernel itself consists of everything. The kernel itself is everything below the system call interface and above the physical hardware is considered the kernel. Provides file system support, CPU scheduling, memory management, other operating system functions. Large number of functions for one level. It's actually kind of huge, you think about it. And here's what it looks like abstractly. And again, this sort of looks like the picture I drew for you last week as well, kind of, sort of. Just more lines. And we have the kernel interface to the hardware. And then we have the hardware. Hardware is the connectors to the terminals, the device controllers, tape drives, memory controllers, physical memory, everything that happens to be installed on the physical hardware. And then we have the kernel interface. And the kernel interface is everything in here. So we've got signal termination handling, I/O handling, file system swapping, I/O tape drive, scheduling, page replacement, all these different facilities. And up here we have the user with their user application programs that are connecting through shells and command interpreters using system libraries. And this is the system call interface that we're going through. This is a huge area of the computer operating system. This is a smaller area. In a Unix environment, we have a huge kernel, kind of kernel responsibility, a very small user level. Windows is the opposite. It's a bitsy little kernel, everything's loaded on top of it. And these are device drivers, interfaces, programs, applications, systems programs. Everything is loaded on top of the kernel instead of inside of the kernel in a Windows environment. Microkernel system structure. So it moves as much from the kernel into the user space. So microkernel is actually the trend. In fact, this is the Windows is really referred to as a microkernel. It just contains the basic Unix functions, or excuse me, Windows functions. Well, okay, basic generic operating system functions. Everything else is outside of it, and everything else gets loaded by the user mode. So the kernel loads up and then says, hey, you have a driver for this? Hey, you have a driver for that? And it asks the user, and the automated in the boot sequence goes out and loads the device drivers and makes the memory available, makes everything available with a very small footprint kernel. When you have that, you have more flexibility. So back in the old days, especially back when IBM came out with the first PC, then we had predictable hardware. And we had huge, monolithic, one kernel does it all. Huge kernel that we can load on there. And the kernel wasn't a micro, it was just a regular large kernel. Had everything you needed. And then we had PC clones, IBM clones. I don't even call them that anymore. But they used to be IBM clones, and that's what we used to call them. And others computers. And the hardware was different. So we had to find support for various different hardware components that were sort of unexpected. How are you going to build that into a single packaged kernel and have it work on every system? Doesn't work that way. Instead, now when you install operating systems like this, Windows is a good example, it looks out for your hardware and says, what do you have on this system? And it finds the drivers and things that it needs, loads a microkernel, and then loads all that other stuff on top of it outside of the kernel. So it can have a generic kernel that supports basic functionality for processors and stuff like that, for generic hardware. But then on top of that, it loads everything else that's specific towards the hardware of that computer. So communications takes place between the user modules using messages or message passing that goes on with the kernel. It says, hey, load this, load that, I need this, I need that. Benefits, easy to extend the microkernel, add new hardware, new features, work with a variety of different hardware. Easy to report the operating system to new architectures as well, which is why a lot of the embedded systems work with microkernels. So we've got itsy bitsy little kernel that just loads up basic functionality and we load everything else on top of it. Because depending upon how much memory and what kind of features we have, we may not necessarily need everything. We don't have to load it if we don't need it. More reliability, less code is running in the kernel mode. More secure, able to customize it. Determinants performance overhead of the user space to the kernel space communication. You have to have some memory from the user mode perspective in order to load everything, if it's not all being loaded by that system's program. So here's the Mac OS X structure, where we have a Mac mock batch kernel BSD Linux system. So this is the kernel environment is actually separated out in terms of the underlying support for the hardware that's specific to the OS X kernel support, the BSD kernel that loads on top of that. And then we have the interface, the application environment, common services, the OS X desktop is always loaded on top of BSD, which is why you can always go to a terminal prompt and talk to BSD. So you really have two in one. You have a Linux and you have a Windows look-alike OS X operating system. And this was just the operating system of the OS X that decided to add the BSD kernel. And so the BSD is actually running the desktop. And so previous versions of before you got the OS X, before we got the X actually, we had 9, 10 previous versions of the Mac operating system didn't have the BSD kernel. So it always ran on top of this though. And this was particular towards the hardware, which was the PC essentially configuration that we were working with, which wasn't IBM compatible, which is different. Now we're using Intel processors and we actually have IBM compatible MacBooks. So now we can actually load Windows on a MacBook without anything. You can just destroy everything that's on there, open up your latest Intel processing version of the MacBook, the current ones that are on the market, and load Windows on it just as if it was a Windows machine. But why do that if you're going to buy a Mac? So use the Mac OS X. You already have it. It comes with it. But you know what? There's a lot of people that do that. There's a lot of people that load Windows on it, no problem. But you can, because it's no longer a different architectures. Now it's Intel compatible, which means we don't necessarily need the same configuration as we had before. Modules. So most modern operating systems implement what's called kernel modules. Uses object-oriented approach. Kernel says, oh, hey, you have USB ports. Let's load on a kernel module to support those ports. Okay. So each core component is separate, and each talks to one another through known interfaces. And each is loadable as needed within the kernel. So overall, similar to layers, but with more flexibility. So we always hear about kernel modules. And kernel modules and Windows drivers. In the Windows world, we call them drivers. Kernel in the Linux world, we call them modules. They're loaded on driver support. Driver module, very similar in concept actually, except modules are more broad. You can have a file system support module, which is more than just a simple driver. So there's a Solaris module approach where we have a core Solaris kernel, and we have scheduling of classes, file system, everything is loaded on. So this is small, and we have modules that we load on top of it. Think of the modules in the Windows comparative. I don't think I have a Windows on here. No, I don't. If you want to talk about Windows, these would be DLL files. How many people have ever accidentally deleted a DLL file and then notice that your system doesn't boot up properly? Or your hard drive can't be found, or your internet doesn't work, or it's because those files were referred to as dynamically linked libraries, aka modules, aka components that are loaded by the kernel. The kernel is the Windows brains that's writing underneath the user mode that says, if we want to send an email message, we have to go through a port, we need a socket abstraction, we need this DLL file. And in the Windows system, we can just have one copy of this dynamically linked library loaded out there, which is why you just delete one file and nothing works. Because you have hundreds of different programs that all look for this one file. And so it conserves space, creates modularity, and flexibility. So when you do an update, you're usually replacing those files with newer versions of those files. They have improvements, hopefully. But those files are important, so if you start messing around with that stuff, in fact, you can mess it up just by removing the configuration information out of the registry. And then even though the file's there, the kernel doesn't know it's there. Because you've removed the link to it or something. which is why people don't mess around with their computers anymore like the old days. And virtual machines. And there's a program that I run on my computer here called Parallels, for which I've installed Microsoft XP on top of. And it's basically an operating system running on top of an operating system through what's called a virtual machine environment. The Java JVM is another very well-known virtual machine environment, which is what JVM stands for, Java Virtual Machine. It's an operating system on top of an operating system. So essentially, the virtual machine is running the operating system, not the underlying operating system. And the virtual machine is just a program you're running. So you run a program like the Java JVM, and you run class files on top of it. So it gives you cross-platform compatibility because you're not running it on Windows, you're not running it on the Mac, you're running it in the JVM. So it doesn't need JVM can be loaded on Windows, can be loaded on the Mac, can be loaded on UNIX, can be loaded anywhere essentially. So the JVM takes the layering approach to its logical conclusion, and it treats hardware in the operating system known as the kernel as though they were all hardware. It takes everything and treats it as a lower level abstraction, builds on top of it, provides interfaces identical to the underlying bare hardware. And sometimes there's little memory issues. You don't get the same performance as if you're running exactly on top of the hardware, although modern day virtual machines are a lot better than they used to be. In fact, I'm really happy with the parallel system. It seems like it's faster actually than some of my Windows books that I have, Windows notebooks that I have XP loaded on. It actually runs faster on my virtual machine than it does on that. So it'll take resources from the underlying operating system and transfer them to the virtual machine. So I'm really one at a time works appropriately. So the operating system creates an illusion of multiple processes, each executing its own program in its own virtual machine environment. The resources of the physical computer are shared to create the virtual machine. CPU scheduling can create the appearance that the users have their own processor machine. Spooling and file systems can provide virtual card readers and all sorts of different things, line printers, all sorts of different abstractions. And the normal user time sharing terminal serves as a virtual machine operator console as well. And here's the example here, where we have the A is the non-virtual machine, B is the virtual machine environment, and A and B both have hardware. And then here we have a kernel and we have processes running, which is our non-virtual machine. In the B configuration, we have the virtual machine. Sometimes this is like the same abstraction. The virtual machine is just a layering that goes on top of the hardware, which is sort of like, if they had a virtual machine operating system, that would be better, I think. And then on top of the virtual machine operating system, you could load Windows, you could load the Mac OS X, you could load anything you wanted. But the way it's working now is this is actually on top of a kernel. It's on top of an operating system. So we have that virtual machine implementation that's inside of an operating system. And then on top of that, we've got 1, 2, 3 separate computers running on one computer. Essentially, virtual machine environments. So I could technically, install many different operating systems on top of my operating system, and then switch back and forth depending upon what I felt like running and using. Only thing to note, however, is the technology is okay, not lightning fast these days. Not the same as running it on top of the hardware in native mode. So the higher you go up, the slower everything usually happens. So in terms of the abstraction. Virtual machine concept provides complete protection of the system resources. You can actually have a virus, which is kind of an interesting thing. You can't have a virus come in here. It's kind of closed off in terms of the abstraction. You're not going to have firewall issues. You don't have anything. Everything's protected underneath it in terms of the software, the virtual machine software. So it's providing that. There's isolation. Permits no direct sharing of resources. And then there's some that you can actually share, like share internet access and stuff like that, in terms of pass-through from one operating system to the other, because they're both still running. So, virtual machine is perfect vehicle for operating systems, or research and development for testing purposes. System development is done on a virtual machine instead of the physical machine. It doesn't disrupt normal system operation normally. The virtual machine concept is difficult to implement due to the effort required to provide the exact duplicate of the underlying machine. So the abstraction is kind of hard to do. Here's VMware. So another popular virtual machine outside of Parallels. In fact, VMware is probably more popular, I think, as a company. They've been around longer. With the CPU, the memory, the I/O devices, the hardware down here. The host operating system could be your Windows, your Linux, your Mac. Your virtualization layer, your VMware, and then your program, essentially, which is going to be, here we have 3 different operating systems running on top of the visualization, the VMware, essentially. And this is acting as your virtual machine to give you this, and this. And so you usually can like switch back and forth and have them all running simultaneously if you want. Requires hard disk space, requires memory in order to flip back efficiently. Here's the Java virtual machine environment where we have the host operating system down underneath, the Windows, the Linux. We have the Java interpreter, the JVM. We have a class loader in the JVM, and Java interpreter in the JVM. So we take that .class file and .apis and everything, and it runs it, essentially, as if it were the operating system. But it's loaded on top of the operating system. So, if you're not familiar with Java, that's how it's running. So operating system generations. I'm not going to go through the entire history of operating systems, but it's actually not that, the history, the family tree of operating systems is really not that deep. It's pretty shallow. They've been designed to run on many different classes of machines. What is the biggest influence on operating systems since the beginning of time? Well, it would be the von Neumann hardware advancements. So when we came out with our current modern day PC architecture, that was the biggest influence. Because if you think of the concept, operating systems have to adapt to hardware, and hardware is the driving factor. So as new hardware devices come out, as an example, tablet computers, cell phones, and we have different operating systems that have to basically adapt to those environments, take advantage of the features. The system has to be configured for each one of the specific computer sites, computer areas. Sysgen program was obtains information that's concerning the specific configuration of the hardware. We have booting that occurs, as more terminology, starting a computer by loading the kernel. Bootstrap programs are code stored in the ROM on the actual hardware that enables you to locate the kernel, load it into memory, start its execution. So, when we talk about system boot, we're normally talking about taking something from code, initializing it from a hardware perspective, and then letting it run, and then taking instructions from it rather than the hardware. So the operating system must be made available just so that the hardware can load it, can share it, can start it. It's a small piece of code called the bootstrap loader. It locates the kernel, loads it into memory, then starts it. Sometimes a 2-step process where we have a boot block on a disk, a fixed location where the bootloader program runs. So when you power initialize the system, execute starts a fixed memory location. So we have firmware that's used to hold it. Every device pretty much runs this way, actually. Something in the firmware that essentially looks for a boot location and runs a bootloader that initializes the operating system. It basically loads the kernel into memory. Your cell phones run that way, your computers run that way, your tablets run that way. Everything pretty much boots that way. So, that was the end of chapter number 2. And for those who come in late, we actually started 3. So, questions? No? Next week, this is pretty much, chapter 1 and chapter 2 kind of go over the main operating system infrastructures, structures, components, jobs, role, the kernel concept. Chapter number 3 starts in with the concept of processes. A lovely lecture on processes and systems programming. And then we have threads that follow that with chapter 4. So next week, when you come in, we're going to be talking about processes, which actually works with the theme of your first assignment. So I'll be going over the first assignment next week as well. That you're probably going to want to get a jump on eventually. So it's not that far into the term, but it's at the point now where people start thinking, oh, assignments? Yeah. Probably want to get started. So if there aren't any questions, we're done for today. See you next time.